of the solar cells are never identical. Even cells from the same batch of manufacture will not have identical IV characteristics. Further, you will see that when the PV cells are mounted on the rooftops and exposed to the solar radiation, there may be neighboring buildings, the shadow of which may be falling on portion of the PV cells or PV modules. There may be trees nearby whose shade will be falling on portions of the PV modules. Therefore, some of the PV cells will be under shade and there will be some of the PV cells which will be under bright sunlight. Therefore, the short circuit current of the PV cells in bright sunlight will be much higher than that of the PV cells which are in the shade. Therefore, you will see that having non-identical solar cells is a practical situation. Now, if these cells having non-identical IV characteristics are connected in series, what will happen? What will be the resulting IV characteristic of the combination? Will there be detrimental effects? Can we estimate the resulting IV characteristics? How is the power versus voltage curve? These are some issues that we would like to look at and study in this module. Here we see the circuit of two PV cells, non-identical PV cells, and that are connected in series like this. And these 2 points are the output terminals of the combined series connected cells. The load is connected across the output terminals R0. We are interested in the voltage Vt across the terminals and the current through the terminals. Vt1 is the voltage across the terminal. Now we are interested in seeing how to get the IV characteristic of this entire combination. So let us have alongside the V versus I graph, still unpopulated, just the X and the Y axis. Let us have also another I and V axis, and this is for having the IV characteristics of cell 1 and cell 2 and how they play a role in the development of the IV characteristics of the combined cell. Now, let us have this IV characteristics. This IV characteristic shown in red is that of the PV cell 1, which is also shown in red here, and the voltage being measured there is shown by a red arrow. The second IV characteristic shown in green represents that of is also shown in green. So I have indicated the IV characteristic PV cell 2 slightly lower than that of PV cell 1, indicating that the short circuit current of PV cell 2 is smaller, meaning that this cell is shaded. I have considered the open circuit voltage VOC1 and VOC2 as same for both the cells as shown here. The short circuit current ISC1 and ISC2 are as shown here, and the green one, that of the cell 2, is a bit lower, indicating that cell 2 is partially shaded. Let me consider a situation where R0 is infinite, which means this is open circuited. These terminal, the combined terminal of this module is open circuited, which means the load line is along the x-axis. In both the cases, it will be along the x-axis because open circuited, no current flowing through either of the cells. Each of the cells are open circuited. The combined cell is also open circuited. So what is the operating point? So you will see for each of the individual cell, the operating point is here because the load line is the x-axis. So the terminal voltages VT1 and VT2 are like this. How does it look like here? So if you see VT, terminal voltage of the combined system, is this plus this. So one operating point that you will get is this, which is VOC1 plus VOC2 with the x-axis as the 1 by R0 load line. Now let us change the value of R0. From open circuit, we will put in some finite value of R0, and if we do that, let us say that some current flows. This is the current line. Likewise, the same current line is indicated here also, indicating that there is some current flowing through the external load, the same current flowing through each of the two cells. Now, I know how much amount of R0 I have applied, and therefore the 1 by R0 line is known. The current line is known. The point of intersection is one operating point. That's all. Now this current line here, with respect to the two individual cells, you will see that the operating points are as shown here. Points of intersection, the respective IV curve. So this distance is the voltage across the cell 2, VT2, and this distance with respect to the other operating curve is VT1, which is the voltage, terminal voltage across the cell 1. This voltage plus this voltage will be the voltage at this operating point here as shown, which is this VT1 plus VT2. Now, let us increase the load further, decrease R0. So you will see that the load line, the slope has increased. This is the increased I0, the load current, and this is the point of intersection. This is the new operating point on the combined cell IV curve. So I get one more point here. For the increased load current, with respect to the individual IV characteristics of the cell 1 and cell 2, you see here are the new operating points, and this is the voltage across cell 2, this is the voltage across cell 1. Addition of this will be the voltage of the operating point of the combined cell. Now I will further increase the load, which means I will further decrease R0. So what happens? This is moving up further like this. This is the operating point with respect to the load current line as shown here, the horizontal line. So this would give you the one more operating point as you traverse, as you sweep the load line from here onwards. So with respect to this load current, you see the operating points on the two IV characteristics of the PV cell is as shown like this, and you see the voltage across PV cell 2 is much reduced compared to that of PV cell 1, and summation of this is what you see here, VT1 plus VT2. Let us see at another critical point when you increase the load a bit further, I can reach at this point, that is the zero voltage point of the cell 2, where you have the operating point exactly in such a way that it is exactly at the vertical axis for cell 2. Cell 1 is at an appropriate point here. Now what happens to the combined characteristic? You see that the load line is like this, and this is the operating point. This will match exactly with this because the voltage contributed by the cell 2 is 0. So you see here, VT2 is 0, VT1 is the voltage that is occurring here, and that should exactly be VT1. And which means that the cell characteristic 1 must pass through that point. So there is a point on the cell characteristic 1 which passes through. Further on, if I try to increase the load or decrease the current I0, there is not much significant rise in the current, because you see that the cell characteristic 2 starts going on to this quadrant. It is not the generating quadrant. This is the only quadrant, the first quadrant is the only quadrant which is generating quadrant or the source quadrant. This is a sink quadrant for cell 2. So the voltage here becomes negative. This is a negative voltage appearing across this, and this is a positive voltage with respect to the cell. So cell 1 is acting as a source, cell 2 is acting as a sink. Summation of this one, VT1 minus VT2, is actually what is this point. And proceeding further, if I decrease this still further to a short circuit, let us say 0, and you make it 0, you will see that the operating point here shifts here for this current. You will see that this voltage will exactly match this voltage such that these two will cancel and the voltage across the terminal is 0. So VT2, which is negative, VT1, which is positive, these two will exactly balance each other out so that you get an operating point here which is 0. Now let us look into some problems in series connecting non-identical cells. One of the main problem is that some of the cells will act as source and also sink. We saw that PV cell 2 under some conditions, operating conditions, was sourcing, and under some other operating conditions was sinking power, which means dissipating, and as a consequence that cell can become hot during that condition and deteriorate. Let us consider the IV characteristic of the combined cell and plot the power curve also in the same graph. So this is the power curve of the combined cell with respect to the voltage. Let me now superimpose the cell 1 characteristic. This is the cell 1 characteristic, as you will see. And the important point is here the intersection of the cell 1 characteristic with the combined cell characteristics. And at this point, if I draw the vertical line, we see that this is a crucial juncture. To the right of this line, you will see that both the cells are sourcing, and to the left of the line, only PV cell 1 is sourcing, PV cell 2 is sinking. So this is the dividing line. Now at this line exactly, if you look at the power curve of P2, this is the power curve of PV cell 2. See that at this point, when the voltage VT2 is 0, the power that is delivered from PV cell 2 is 0. So it's now stops behaving as a source. And if we go still further down towards the 0 axis, it starts behaving like a sink. It's a dissipator in these regions. Now, if you consider this portion of the characteristic, the combined characteristic, which is shown lightly shaded, reflects onto the second quadrant for the individual cell of the PV cell 2 in this case. And the second quadrant is not a sourcing quadrant, it is a sinking quadrant. Only the first quadrant is a sourcing quadrant. So if a cell is in the first quadrant, the operating point is in the first quadrant, then it is a source. Otherwise, it is a sink. That is what is happening to the PV cell 2. To the right of this line, the PV cell 2, the operating points are in the first quadrant, and therefore you will see that P2 is positive. To the left of this line, when Vt becomes 0 and negative, the operating points for PV cell 2 is in the second quadrant, and therefore you see that it is acting like a dissipator. Contrary to that, you will see that PV cell 1 is positive in both the regions of the IV curve, and therefore it is always a source. Now, if you look at it, is more or less constant. This can be seen from the fact that for a variation in the current in this narrow region, narrow space, the variation in the voltage of PV cell 1 is not much, and the variation in the current flowing through both the cells is also not much, and essentially the product of I into the cell voltage is essentially constant, and that is why you see almost it is a constant. And you see that here this power balances out, the negative power and the positive power gets balanced out, and therefore the power of the combined cell is 0 at that point. The important takeaway is that cell 2 acts as a sink during a portion of the IV characters of the combined cell, and that is detrimental to the PV cell 2. It deteriorates its characteristics. Not only that, it becomes a dissipator, and it dissipates this extra power and thereby brings down the efficiency of the entire system. So we should find ways to avoid this problem as best as we can. Non-identical PV cells, when connected in series, have some issues. The two PV cells as connected here are now acting as sources. Notice the polarity plus minus, both are in the same direction, and they aid each other, and both are acting as sources. They are operating in this region of the IV characteristics, where power from both these cells are positive. Now, if one of the cells is partially shaded, we see that during a portion of the IV characteristic of the combined cell, one of the PV cell 2 here for this example, shows negative power, indicating that the PV cell 2 is acting like a sink. Under that condition, this plus minus polarity will get reversed like this. So now PV cell 2 is acting like a sink or not is acting like a sink. PV cell 1 alone is a source. Now we can slightly modify this circuit so that it is much more convenient to read in this fashion. It is still the same circuit. This PV cell 1 is a source, and you have a load R0 plus minus as shown here. You have another PV cell 2 acting like a load, additional load plus minus the same direction of the load as shown here. So now the PV cell 2 here is acting like a sink or a load, means that it is operating in this portion of the IV characteristic. We can as well replace this PV cell 2 by a resistive item like this. So in effect, PV cell 2 is behaving like a resistor during the time when it is sinking. Now the question is, the PV cell 2, if it is sinking, it is dissipating and it is becoming hot. Can we avoid that? Can we bypass the power? Can we bypass the PV cell 2 or any cell which is sinking such that it doesn't consume any power during the time when it is normally supposed to behave like a resistor in this region? So this can be achieved by putting a diode across like this. So whenever the PV cell, in this case the PV cell 2, reverses polarity and operates like a sink, we have plus and minus. So we have put a diode here, and the diode will get forward bias and conduct. Note here, for the sake of simplicity, right now I am considering this diode to be ideal. Its cut-in voltage, turn-on voltage is 0 volts, or very less compared to the PN junction voltages of 0.7 volts of a single cell. This is very important. I will explain that a bit more later. For now, consider that this diode is ideal and the cut-in voltage is 0. So the moment the PV cell 2 reverses polarity, the diode cuts in and bypasses the PV cell 2. Thereby, you will not have any power dissipation within this cell and the cell won't get hot and deteriorate. Now, let us look at this characteristic. What happens when we put this diode? There will not be this negative power. So that portion will vanish. So which means all the powers are positive. The PV cell 2 will only source power during this time, and during this time it does, during the time when it was sinking earlier, because of the presence of the diode, it will get effectively bypassed by the diode. Now, if you consider this characteristic during this portion of the